Another draft physics video presentation. So mostly on the subject of gravitational lensing. And there was sort of an interesting post by Mindless Marbles, who's, a despicable troll, but now and then, says something reasonable. So it's a counter argument I'll deal with. And then there was this video posted by somebody called American Slave. I think that's sort of an exaggeration. But anyway, I would have given him the benefit of the doubt, frankly. I played most of his video. I said, okay, got that wrong, got that wrong. Um, you know, um, but then he said some shit in the comments that just, were such a turnoff. You're just like, okay, forget it. Screw the benefit of the doubt. So at this point, he says some kind of, so this is, he's arguing, I have pointed out that Einstein's equivalency principle is flawed, in my opinion, for obvious reasons. Okay, so the first obvious reason is that any one of you, should be able to kind of understand, okay, that gravity, okay, is a force, okay, that actually is moving the tiniest bits inside of you. So whatever the force it is, it's very, very fine kind of force. It doesn't like hit you in the head and then hit you on the shoulders and then, it doesn't push on you like a physical person. You'll never feel gravity pushing on one part of you, so to speak, like, oh, it's pushing on my hand, or it's just pushing on one thing. It's a tiny little, whatever it's made out of, it's so fine, and it's hitting the little atoms inside of you, and it's moving the little atoms. All right. Now, obviously, then there's other forces you feel, like if I just take a telephone pole or something and I, go 30 miles an hour with a telephone pole right at you and I hit you in one location, obviously the force isn't going to be in, hitting every little bit of you, the little bits. It's going to hit the matter of you, and it's going to dent you, and it's going to cause all kinds of a different kind of acceleration. So your acceleration by gravity and your acceleration by telephone pole hitting you is not going to be, it's kind of silly to say it's the same thing. It's really not the same thing. This force has to go through the matter. It has to start in a one location on you, one place. I hit you with a hammer here on top of your head. Okay, I mean, it's, one of my favorite dreams. And, I bash your skull in and, deform your head. You might not even feel it down here at your toes, right? Where gravity is guaranteed to get all of you, right? I can mash you with acceleration, with a force, and the force won't even get to all your parts because of the fact that I put it in so fast and I displaced so many atoms and I used up all the energy. So it's kind of stupid to say rocket engine, okay, moving floor, okay, and that's all it's doing really. Moving the floor is the same as, Earth, standing on Earth, being affected by gravity. It's not equivalent. We really shouldn't go, oh yes, equal sign. No, we should go, not necessarily exactly the same thing. So there's no reason for this equivalence in the first place. And then secondly, what Einstein did was get the formulation kind of, in my opinion, back assward, okay, and not appreciating that when the rocket ship is moving half the speed of light, let's say, and I shoot photons across, the photons aren't being affected by a force. They're not doing anything. They're not changing at all. And the ship's surface, the target I was aiming for, okay, that target moves away, okay, and I missed the target, right? So I hit below the target and I say, oh, look, the light bent and hit below the target. No, it didn't. That's an optical illusion. That didn't happen in any reality anywhere. The light went straight across. You move the surface. So there's no force acting on the light. And yet he said, okay, let's make them look the same on Earth, so I'll make light bend on Earth, And I have to make it bend a lot more than normal because, it's not going to work. It's not going to bend enough to be anywhere near equivalent to this. I still think it's equivalent, actually. 2xing light doesn't really get you to equivalence to the rocket ship example. But anyway, So this is sort of this logic, and I'm saying this logic is fundamentally flawed. So here I'm saying, you're telling me you have complete evidence, you have some reason to believe. I'm saying you have no reason to believe. So what do we know about forces? We know you can't bend them. We know that two electrons, okay, that are going to interact with each other, the force from one electron has to reach the other electron for there to be an action. It has to travel the speed of light, reach the surface of the other electron before the force can have any effect. And likewise for the force sent by this electron, it has to reach the other electron. The two forces can't hit each other. Forces don't bounce off of forces. They never hit each other. So you really do have to believe that, gravity, a simple process of things moving towards each other, just sort of like half a magnet, right? I mean, gravity's like half a magnet. It does half of what a magnet does. It does the attraction thing. And you actually believe that this attraction from gravity is fundamentally different. Not just superficially different, but fundamentally, completely different mechanism than the mechanism that attracts two magnets. So two magnets would attract the attractive force. You're saying that those two things have no equivalency. Nothing. There's nothing like each other. Because obviously this charge and magnetism doesn't do force bending force. You can't bend the stuff moving the speed of light. It has to interact with a piece of matter. The stuff moving the speed of light has to hit a piece of matter before it can go in some new direction. It can't be just bent. All right? There's no evidence of it. No other experimental evidence. So first you have to believe, okay, light is a special force. Gravity doesn't bend magnetism. It doesn't bend the electric field. It doesn't bend any of these other fields, but it does bend photons. So you think photons are somehow special. There's something special moving at the speed of light. And the only thing we know that's special about them really is the fact that it has a frequency. And why would having a frequency make you more bendable? So that doesn't even make any sense. So you see no correlation between, all the forces move the speed of light. Gravity, magnetism, photons, all this stuff moves the speed of light, and yet you think, oh, it's fundamentally different. Photons are fundamentally different than the other forces. Even though we kind of see in experiments, we can't bang two laser beams off each other. We can't make the force bend the force. So anyway, so even with that evidence saying, I don't think so, you're saying that you have strong reason to believe that photons are magically special. They're different than all the other forces, different than magnetism, different than electric field, different than all that stuff, and you can bend them with gravity. Okay, so first they're different than all the other forces, and now they're different than all the other matter too, because then we know all the matter bits are bent a certain proportion, a certain amount. And photons are now bent twice as much as that amount. That's Einstein's theory. Okay, so maybe you don't know that, but that's what Einstein changed in his field equations. He made light twice as bendable. That's because of the equivalency principle. So that's the premise here. Okay, I mean, Eddington wasn't trying to figure out how much an electron was bent by, say, the sun, because Eddington, the amount it would be bent would be too small. The number would be, 0.68, and instead, because of Einstein, he can go now 1.2.8 difference, or whatever the exact numbers are. So he has twice as much deflection possibility because of Einstein's theory. He couldn't even do his experiment. There'd be no theoretical hope of doing it if it wasn't for the fact that Einstein 2x'd, the effects of gravity on photons. So you're saying you have good evidence for that. I'm saying you don't really have good evidence for it. Okay, the evidence basically sucks. And all you have as evidence is the Eddington experiment. Now, I say, it hasn't been successfully repeated. Yes, there was 2 attempts on 2 different eclipses to do the experiment, and they both failed for technical reasons. Okay, one of them was because of a kind of, a reason why you just don't bother even trying the experiment in this circumstance. The eclipse was way over here on the horizon, okay? So you have to look through so much atmosphere that you're screwed. That's what's sort of remarkable about the great eclipse just a couple of years ago over North America, is that it was a 12 noon. I mean, it really was 12 noon eclipse. I mean, it's very rare to have a perfect 12 noon eclipse. Really short amount of an atmosphere you have to go through, so you can get really good results. And over all the telescopes, how many 12-inch or better telescopes were there across all of the United States, right? Here's the United States, across this whole hunk of the United States, from here to here. Well, actually all the way up to Seattle up here. You don't think there's a few of these 12-inch or better telescopes? Not one of them could do this experiment? I mean, it's a laughably, silly. So yeah, one amateur guy did it with a 4-inch telescope. Wow. And that saw 50 stars. Okay, that's how good the resolution was. He saw 50. Right? Eddington was hoping for 10,000 stars on his photographic plate, right? 10,000. So we have a resolution degrade, okay, of whatever, 90%. We have a resolution degrade of 90%. More than that, 95%. Anyway, it's a huge resolution degrade. So with our modern technology, 100 years later, the best we can do is do a 95% less resolution experiment. Oh, great. So obviously he says he did it, but I obviously contend that he didn't have nearly the instrumentality, the technology necessary to do the experiment. He was just looking at big, giant, here's a big, giant pixel, and here's a big, giant, I mean, he didn't have any hope of seeing any images, really, or getting anything exact. Look, I got 2 pixels. Okay, I'll say the thing's there. There's no theoretical reason to believe that it's there out of a sample of 2 pixels. So there's no point in going into it. But yes, it's never been repeated. Just a fact, okay? And then you have this huge advantage of doing it from space. If you do it from space, the sun is black here. Just pure black. Just there's no atmosphere, there's no haze, so there's no bullshit. So you don't have to worry about all that crap. You still have to worry about the fact that the corona is still there, even though it's invisible. The corona is still there, which means there's a bunch of charged particles around the sun. And obviously, if you look through there, you can get all kinds of scatter results that'll look like the real thing, but they're not the real thing. So you really can't do the experiment in the sun's corona. But obviously, from space, you have a huge advantage. You don't need an eclipse because you don't have to get rid of all of this haze around so you can get the black space next to the sun, so you can see the stars. Okay, all sitting there right next to it. So you don't need an eclipse. You can do it any day. So huge advantage doing it from space. I mean, first, you don't have all the haze of the atmosphere, but you also don't have the brightness of the atmosphere that just ruins the function of your telescope. Obviously, you can't use a telescope during the day to look at the stars. So you can't have the sun visible and then look at stars. I mean, obviously. And eclipses are far from perfect anyway, so, obviously from space it's a huge advantage. I don't know exactly how big, 150, 100, I don't know. Big advantage, though, percent-wise. You've eliminated so much of the impediments to getting accurate results. Alright, so anyway, so he doesn't quite get that history right, doesn't really understand. So he's asserting that I have to understand that gravity affects photons twice as much, like somehow there's a good reason to believe that. And I just explained there's no good reason. The reasoning is completely flawed, unless you think light does bend in the spaceship. That when the spaceship does this and zooms away, okay, from the beam of light, that somehow the light bent. The light bent and hit the back here. If you believe that, well, okay, I think you're kind of silly and stupid, but, I mean, if you believe that's what happened, the light didn't bend in the spaceship. There's no bending at all. So, why do we think it bends on Earth? There's no good reason. Anyway. So, alright, so we'll play a couple of points in this video. So he goes reading his textbook, blah, blah, blah. It didn't say anything specific, didn't cite experiments. There wasn't, there's no interesting data at all. So it was rather pointless. So we'll jump to 1830 is where I started saying, oh, well, I guess I should respond to some of this crap. I don't hear anything.
Then you have this.
There we go.
So this here. So if this guy isn't so strong, we only know the light will lose.
So he's talking about black holes, which, again, theoretical mush, really, no hard evidence of the existence of any such thing. And certainly there's no hard evidence of light ever falling into one and being bent by one. So this is more crap. So he's just saying I should believe that light is bent, okay, that somehow they've proven light bends in gravity. I'm saying, what's the evidence for that? Oh, there isn't any.
Because this gravity is too strong. But if it's not, doesn't it make sense that it would bend? And isn't the bending?
No, it doesn't make sense to me. So you're saying it makes sense that photons bend. Something moving the speed of light bends twice as much as electrons and protons and other pieces of matter. So if I'm going with a piece of light towards the sun, let's say we're both flying together, the photon gets bent twice as much as I do. I keep going sort of straightish, I miss, I don't go into the sun, but the photon does go into the sun. That's the argument, okay? And I don't see any reason why, yes, it should be that way. No, it doesn't make any sense to me. I'm sorry it makes sense to you.
Called gravitational lensing. So I don't know. I can sit here and read all this stuff and we can try to figure it out. But I think it kind of rests on the fact that you think there's something wrong with the equivalence principle.
Yeah, I explained it now twice or 5 times or maybe 17 times. I think there's something wrong with the very idea of saying getting hit in the head with a hammer is the same as being hit by gravity. The two forces aren't the same in how they're being applied and how they move through your body. So yeah, I'd say there's no point in saying those two things always create the same result, because they don't.
But they use the telescope to double check all this, right?
So you say they did, okay? So again, so I have to believe it because you say they did. You're not showing me that they did.
Let's continue.
Piece of matter in the universe, and mostly just electrons and protons, because they're really the only other pieces of stuff. There's force bits and then there's the matter bits.
Alright, well, I guess I don't know why I don't think that's the relevant part, so I'm going to move ahead to, well, we're almost there, right? Well, so I might as well just play it.
So it's basically saying force bits are bending gravity. Now, the first proof is the famous Eddington experiment, which is just terrible science in the sense that it's marginal, even if under perfect conditions. It's clearly done under incredibly imperfect conditions. It's they approximate it to be something like measuring a human hair's worth of difference in an object at, say, 30 feet, which is a pretty delicate measurement. And again, done under really lousy conditions, 10% of what they were of their expectations. But yes, hailed as proof, Einstein is correct because they found enough deflection in a time-lapse photographs taken over, I think, a 7-minute period of time. So just blurry smudges on a film, and they found enough.
So I wonder if he paid any attention to this. So you do understand that's what the experiment is, right? I mean, the Eddington experiment, even in perfect conditions, it's a time-lapse photo. So what you're seeing isn't a little round star in a location. What you're seeing is a little blurry blob going in a direction, okay? And then you have another, you have blurry blobs. And what you're trying to do is figure out where the center of the blurry blob is, okay? And then try to measure that distance and see how much those distances have changed. So it's not some simple experiment.
I think reasonable reasoning to be skeptical of the quality of that experiment. Yet the promoters are just so aggressive in saying they proved something when they haven't. So famous New York Times headline, Einstein correct. All of a sudden, relativity is a true theory just because they found one correlation. All right, so then later, time elapses, and then they get these.
So again, the history is that yes, Einstein gets a New York Times headline, Einstein right, based on the Eddington experiment, which was incredibly flawed. The guy says in his own journal, I wouldn't stake my life on these results. It's a part of the public record that his expected results were far below, the data was far below the quality he was hoping for. Like 90% below.
From space, and they see these phenomena. And so let's just point out the Eddington experiment never successfully repeated from an Earth-based telescope with the same quality of instrumentation. And
how do you know that? Because
so again, how do I know that? I'm saying there's no public record of it. It's unfindable. You go ahead and find it if you think it exists. I have looked. It doesn't exist. I have to prove it doesn't exist? Is that your standard? I have to prove the experiment doesn't exist. You don't have to demonstrate that it does. Oh, that's silly.
I just think that's false.
Well, who cares what you think? Okay, let's see what you can demonstrate with evidence. I mean, not to catch on that you have to have evidence in this argument is, kind of silly by now, frankly. All right, maybe you're a newcomer here and you don't think that this is a conversation about evidence, but yeah, that's what it is. It's a conversation about evidence and somebody producing some.
I think that's false.
Never done from space. Even though space Eddington had to use a solar eclipse, your eclipse has to be hot.
I think that's false. I think that's false. Who cares? Again, so what? Where's your data? Where's your evidence that it's false?
In the sky, or too much aberration in the
Right. So basically, in order to prove Einstein right, they did the experiment on the ground. But you think that's stupid because there's so much in the way, and it makes sense because the atmosphere is going to get in the way, and that's going to distort things, and it's not a good idea to do it on the ground if you can do it in an environment where that doesn't happen, which is why you said you can do it all day or all night.
Atmosphere,
Yeah, duh. And so how you responded to that? You don't think it's not interesting to you that this fundamental experiment that got Einstein in the New York Times, that turned him into a public figure, that made him respectable, that somehow they don't have to repeat that experiment. When isn't repeating experiments fundamental to your science?
distortion. So it has to be a good eclipse, like the one we had in 2018 or whatever it was. Almost perfect over North America, yet nobody with a big telescope did the experiment.
Okay, how do you know that?
Well, because I looked it up, okay? So that's how I know it. What do you think the answer is going to be? I just made it up like you just make up your opinions and then spout them? No, I went looking for it. I had other people go look for it. Other people looked for it. They can't find it either. Okay, the only person apparently who published any public documentation regarding doing the experiment was an amateur astronomer, okay, with far inferior equipment, period. That's it.
I mean, if you're just talking, I'll let it slide, but how do you know?
Again, what do you mean, how do I know? What do you think the answer is going to be? Well, I looked and I can't find it. Is there some other how do I know? Shit.
So we didn't do it with photographic images or anything like that, so, never...
I mean, the standard, can I do that to a physicist? Can I just keep saying, how do you know, how do you know, how do you know? Everybody's assertion I should just keep doing that? I mean, what is that crap? You have to counter it with a counter argument made out of, says you. Yes, says me until somebody says different with something called a piece of evidence.
So,
again, never is a really strong word. Yeah.
Oh yeah, and what is it supposed to mean? I mean, I can just change something. I can say, you're really 4 feet tall and green. You were never anything else other than that. I mean, there's things I can say never, and I can be pretty confident. So again, just more horse shit.
Experiment made Einstein household work, never repeated successfully. And the whole space argument is that if you use a telescope in space...
All right, well, anyway, didn't get to this part yet, so I won't bother. I mean, just the whole idea that somehow I have to prove the evidence doesn't exist by showing you every Google result ever compiled or something. What, should I just do every single Google result and show you how each one of them doesn't have that experiment in it? So I'll show you every piece of paper on planet Earth and show you that none of the piece of papers has any documentation about doing the experiment. Fuck. But what exactly do you want as proof? Well, anyway, so he made a comment here that just pissed me off, so I said, fuck this asshole. That's sort of how it works, frankly. It doesn't take much for you to turn into something I don't want to know. Let's do this newest first thing, because sometimes you can't see a comment until you do that. Alright, so this K guy says, I wouldn't recommend watching Amendum Draft Science channel, to be honest. Oh, I'm so disappointed. It's all theory talk. Well, yeah, theories that make sense versus theories that don't. And there isn't any real fact-checking. Well, there's just as much fact-checking as you douchebags have done. So where are your facts, considering where, you open one slit and then you open a second slit, and where photons were, they stop being there? Where's your fact-checking there? Where's your real hard evidence of that fact? Where did you ever check the facts? Oh, that's right, you didn't do any of that. Don't want to learn things that are false. Like what? Is it false that the Eddington experiment sucked? Is that false? Is it false that Einstein contrived a twice increase in the strength of gravity on photons and photons alone? I wonder if neutrinos are twice as affected. Are antiparticles twice as affected? Are any? Well, I guess photons have there's antiphotons, right? I guess antiphotons are also twice as affected by gravity, huh? Silly nonsense when you think about it. It's just so silly and stupid that I have to even argue this crap. In my mind, if ethylism, so why the fuck is he bringing up that? Rest on his understanding of how the material world is created, then I have to throw ethylism into question. I mean, what an idiot. I mean, it's just so fucking stupid. Okay, I think Einstein was wrong about bent space, but I don't think Einstein was wrong to hate the Nazis. Yeah, what the fuck? But I should, right? I should doubt. Yeah, I should doubt whether Einstein knew anything about that either. Wow, you're just such a fucking troll. Anyway, this is a big learning experience for me. Well, it seems like you're also, what you've learned is how to be a troll and say, talk shit. That's what you've learned. All right, there's no mystery here. Gary just full of shit about literally everything when it comes to physics. Gravitational lensing doesn't fit his theory. And no, it doesn't fit logically. I'm just saying it's a bizarre claim. So you're making this claim that this one single force, okay, of all the forces, these photons, the one single thing that's moving the speed of light. There's only one thing moving the speed of light that's affected by gravity. That is photon, okay? And then you're saying, and the photon is twice as affected by gravity. You don't think that's the extraordinary claim. You think that's somehow, that's what we should perfectly expect. Yes, two complete oddities. So we have a world that has certain consistent rules, okay, and you're saying there's a special jackrabbit, okay, that grows a turtle shell, okay, and then starts walking really slow like a turtle. Twice as slow as a turtle. I mean, it's an extraordinary, what you're saying. And I'm saying, well, until we see extraordinary evidence, or we see something like ordinary evidence, I don't think there's really good reason to believe that crap. Because it was just made up crap. I mean, it was just theoretical mathematical equivalency crap. Einstein made an equal sign, and then he said he had to make, there's this much bending here, I have to make this much bending over here. That's all there is. And you're saying, that's the good science. Yeah, that's how good science is done. Okay, I'm saying that's crap. Alright, so now on to the mindless marbles. So, screw you, fucker. Yeah, that's what I'll say to him. I might as well do it while I'm here. I'll do the official blocking. We'll go to his channel. And then we'll go to this. I'll show you how to block somebody. And then you go to the About page, and then you get to this little flag, and you go, fuck you. Alright. Simple enough. Jesus Christ. Might as well close the tab while I'm here, because I only have 643 tabs open, so might as well close that one. Don't need all that extra. Ugh, Sean Carroll. Jesus. Somebody suggested I should play some Sean Carroll videos. Yeah, I've already done that. But his videos are so abstract and useless. I mean, he says, videos for the common person, right? It's just so funny, because, who the hell? The common person who wants to sit... it's a Hamiltonian, mathematical equation. Who wants to do a Lagrangian or Lagrangian or something? Oh, sure. Yeah, that's real physics. Oh, fuck. You can't even argue with it because it's just so abstract. Look, here's the, what do they call the that stupid Schrodinger thing, right? And they make this little symbol, and the little symbol represents all the facts known about this object times lambda. Yeah, all the facts known about this object times lambda. And you'll get the right answer. I mean, it's so fucking silly, you know, that it's not a real thing. This stupid forky symbol. It's not. It's not a thing. It's every fact you could possibly know about the object. Oh yeah, sure. And I'll multiply that times something, and that'll somehow make sense to you people. Well, it doesn't make any damn sense to me. Ugh. So now I gotta find the troll. Yeah, that's the troll. This should be the video. Nope, it isn't. So I guess I have to open the video again. I thought I had already opened it.
Okay, and we are recording or watching the shit.
So, yeah, the retard show. Anyway, so I'll get to some other drama maybe some other time with some of these commenters. And again, their invasion of my privacy and whatnot and blah, 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 blah. Surprising fuck asses who comment on this fucking bullshit. Yeah, so it's a good place to go if you want to get blocked by me, actually. So mindless marbles. I said some sort of horror shit. Let's see. So it must be in one of these replies somewhere. And Stephen Bro chimes in with his horse shit. Like another idiot. Alright, where is it? Let's see. He also refuses the laser experiment. Again, he's bringing up that crap. How do I refuse it? So again, these are people who just don't want to deal with any of these questions. You know, it's like the real LIGO. They talk about the 2 mile long tunnel, right? Nah, it's not what it's about. They're bouncing the photon back and forth 1,600 times in that 2 miles, right? See, they thought, well, if we make it a mile long, that'll be enough. Then they figured out, oh yeah, theoretically a mile isn't enough. 2 miles isn't enough. We need 1,600 miles. No, we need 3,200 miles. We need to travel the photon. See, but that creates more wavelengths, you see? More little notches. And they think they're measuring something. I mean, it's just such a joke. So anyway, where the fuck is the mindless marble comment? Not there. Not there. Not there. Not there. Oh, this is going... Okay, I think it's here. There we go. Okay, so he did write a whole long treatise on the lensing argument. And it's not all bad, actually. Okay, so he has an image here. I have the image in here. And so I haven't really read all of it, but he's... Okay, so he's debunking the idea that, okay, you have to have a magnifying lens. And, okay, the argument can be made that, yes, you can magnify in different ways. But let's understand what the principles are, okay? So the basic idea is that there's two things the lens is doing, right? A conventional lens is doing two things. It's taking an object that's small here, okay, and essentially it's making it big. It's giving you a place to project the image of the thing, right? So the image is being projected on this big surface. So you're really just making this thing really big in the lens, and then the lens is going to send all that data to the small location. So instead of looking at this from your real perspective, right, there's line here and then there's your eye here. Instead of looking at this and having to see it from this position in space, essentially what the lens does, it allows you to see it here because it projects the image this way. It makes it bigger. So it gives you, it moves this closer to you essentially, making it much bigger so you can see it better. So that's the idea of a magnifying lens. So the idea is basically you want to collect more light is the one priority, right? You want to make you're collecting more photons, and then you want to send more photons to the person. So lensing has to make, there's two things. There's brightness, you know, how bright is the object, and then how visible is the object. So there's two things you're trying to improve by magnifying. So the magnifying lens actually does two things, though. It's not only taking, you know, it's not even taking this object and making it big, okay, but it's also takes the light when it does that, and it compensates for the fact that this distance is much longer than this distance. So you wouldn't be seeing the same photons, right? But the lens just happens to slow the light down going through the glass. And so you go through much less glass here, so you don't slow it down. And so you do slow it down here on the straight line, so you end up making these equal again. So now you can see the object as it is, because you're seeing all the photons from the same time. But a gravity lens isn't going to do that. So the key to understanding a gravity lens is that it doesn't have the ability to do this time fixing thing. So when you take photons that have traveled very different paths, they're very different photons in time, which is another problem. All right. So this image of his, the only lines that really matter are the two blue lines that go to the person's eye. And so, and then the image, you can understand the drawing of the candle, the object, and then the eyeball. And the idea is to find some way to magnify. What you need to do is to create some place in the universe where you can project this image bigger than, so if the object, like a galactic cluster or something, a cluster of galaxies, that's really big. So you could stick that object in here, okay, and you could say, yes, I'll project the object this way, right? So now you're projecting it onto a much bigger thing. But the fact is you're not really projecting it like a regular magnifying lens. You're only projecting it to one part of the lens. Okay, so like when you see a magnified image, like say if this was a magnifying lens and I made a giant little ant or something, right? I make the ant super big. The fact is that I've made, the whole ant super big, right? So in this part of the lens, I have an enlargement of its foot. And in this part of the lens, I have an enlargement of that foot. And I have its antennas over here enlarged in that part. So each part of the lens is, you could break it into a little tiny lens and still see his foot, technically. So again, it's about making the image big. That is, projecting it on something that you would think of as like a virtual screen. So the little ant is over here, right? I'm projecting it onto the lens, and the lens is virtually sending me that image. It's sending me a virtual image in space. So it's like a screen. It's projecting an image, and then I'm seeing that one image because it all comes to a focus into my eye. Right? So that's sort of how you have to understand how this thing works. So that's part of the context. So his argument is that with the wrong shape lens, that is a lens that bends more in the center. So the regular lens bends more on the outside, okay? Out here the light is bent more, and in here the light isn't bent at all. And gravity does exactly the opposite. Gravity bends stuff a lot here, okay, and it bends stuff a little out here. So it's exactly the opposite in principle. Alright. But he says you can save it by doing this thing. So let's say I have a gravitational object, and I have gravity that's going in this direction, that is more bending as you go towards that center. Then I could have light photons from the bottom of the object can go project here, and photons from the top of the object can project here. This would be less bending, and this would be more bending here, right? Yeah, I have to just move this down, and then it'll look like more bending, I think. It still looks like the same amount of bending, but anyway, the idea is that you're just using a part of the lens, and the light coming from the bottom you're sending here, right? Yeah. And the light from the top you're sending here, and this is more of a bend than that is. That still isn't quite, that drawing doesn't make sense actually. Yeah, it's not more bending. Well, anyway, let's just say this is true. Okay, so it's more bending, and so then, but the point is gravity is this inverse square thing. So the amount the gravity is degrading, okay, as I don't even know how to draw that curve. it's always every bit of distance is a significant drop in the amount of gravity, and you have to think about it as if the photons are traveling through space, right? And and as they're traveling, they're going into a bigger and bigger pile of space. So it's like diluting something. So it's like me dumping this chalk in a glass of water, or me dropping this chalk in a swimming pool. As the volume increases, the weakness of the chalk gets weaker and weaker as a pollutant. So the further you go in space, the more space that's between the photon and any other photon. So the space between the bits of the photon is sort of, you could understand, is expanding, and it's getting more and more diluted. And it's diluting in 2 dimensions. So when something's being gravitationally lensed, right, the idea is is that the gravity is getting weaker because it's going in 2 directions of weakness. It's the space is getting bigger this way and this way. So even if the photon's going through 1 dimension, the other dimension of the space is still expanding, and the photon's getting smaller and smaller and smaller relative in that dimension. So even though it's in the gravity for a long time, it's in gravity that's really, really weak because it's really, really far from the thing that has gravity. And the argument would be is that there would never be enough gravity to make this big a difference, in the angle of bending. And you'd also have the problem that one line, this line is obviously going to be shorter than this line, right? So, and the difference in the length of that line is, sine theta, angle, blah, 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 blah. But you could talk about this as being, this is a galaxy here, and this is a galactic cluster here, a big giant thing. Because that's the only way you can enlarge the image. So that's the other problem you have. See, nothing actually gets smaller or bigger in space. So when something moves away from you, it's sort of an optical illusion that it's smaller. It never got really smaller. It's still producing the same number of photons, but it proportionally looks exactly as weak as the photons are diminishing. So its size is pretty much a representation. The change in its size, just like this hand, is a representation of the reduction in the number of photons that are getting to you. So if you're going to see something and far away, the first thing you have to do is you have to see, if you looked at it plain, you wouldn't see it because it's too far away. There's not enough photons getting to you. So you could never take an object, say this size, and make it into a smaller location. You would always have to project the object onto a bigger surface. So again, like I said, a galactic cluster versus a galaxy. So whenever there's a lensing image of an object, like a sun of some kind, and then there's, their little Einstein ringy thing that's never very perfect, that couldn't happen because the object is smaller than the object you're seeing. You couldn't see a galaxy in the lens of an object like a black hole even, because the area is too small. You're not making the image bigger. You didn't project it onto a bigger screen. So you always have to be projecting the image. To have magnification, you have to project the image onto a bigger screen. And the bigger your screen is you're projecting it onto, you can sort of understand, then the length difference between these lines gets longer and longer. So the problem is that when you look at something, okay, so something would be here, the first bit would, okay, you get that photon, but all the other photons, the object is going to move, okay, by the time you're going to be able to see it, the photon can receive the photon. This photon is going to be 10,000 years later, and this one's going to be 100,000 years later. You're going to get photons from much later times, which means the location of the object has changed, and so you're going to get a mess. So having discrete little stars in an image, not really practically possible. So at any time the galaxy, you can even see the stars in the galaxy. There's no practical way you could do that because the time difference in the photons you're getting is pretty dramatic. Because we're talking light years here. So we're talking about hundreds of thousands of years worth of difference in the age of the photon, which means the position is 100,000 years different. In fact, where the photon left from is going to be very different than where the other photon left from. Where this photon left from is going to be a very different time than when this photon left. So that's another problem. But the big one is you have to project it much bigger. So none of the images that you'd say it's a small thing here, like the center of a galaxy or something, it would be much too small to make another galaxy. The galaxy would have to be projecting itself smaller to be lensed in that lens. It would have to be, the image would be, you're projecting a smaller image than the original object. If it's a galaxy inside a galaxy. So you always have to be projecting the image on a lens that's much bigger than the object. So if you're going to look at a galaxy, the gravity has to be in a whole giant cluster of galaxies. Now the problem with that is a cluster of galaxies, by simple math equations of gravity, are incredibly undense. Okay, like the sun. The sun is huge, 1,000,000 times bigger than the Earth, 1,000,000 times. But its surface gravity is only 70 times Earth's. Well, it's only 7 times what it is on Earth. It's 70 meters per second per second. So it's only 7 times. So the Earth is this big, and the sun is only 7 times more gravity on the surface of the sun. That's an incredibly asymmetrical relationship, right? So obviously the sun is less dense, right? There's a lot less, there's more empty space in the sun than there is empty space in the Earth, okay? The matter bits are more condensed inside of the Earth. So the Earth is much more compact. Now when you have a galactic cluster, I can't even describe how there is a ton of empty space. So there's little clusters of galactic matter. Now the galaxy itself is a bunch of stuff with, very sparsely mattered. So the proportion of space, empty space, to actual matter in a galaxy makes the sun look incredibly like gold, like lead. Okay, by comparison, I mean, even a galaxy is full of air, full of empty space. And the cluster, the empty space, is gigantic by percentage to the amount of mass. So the amount of gravity is infinitesimally small created in this object. And, there's just no theory for light being bent. So now people have used this, I just want to be clear, but the photon is traveling through the gravity and it's in the gravity for 100 million years, right? So there's lots of time for the very weak gravity to bend it. But again, as the argument points out, as my argument points out, okay, the amount of time in this dimension doesn't mean much when the other dimension is expanding the amount of empty space in the other dimension. So you're only consolidating in one dimension. You're only increasing your exposure in one dimension. The gravity is weaker in both of the dimensions. In the other dimension, this is irrelevant. So the amount of the weakness is still it's this incredibly weak amount of gravity that you're actually able to hit the photon with. How to say this? So you have a target, and you have to understand your bullets aren't just scattering this way and scattering this way. They're also scattering this way and that way, okay, into the board and out of the board. So you have to understand that, yes, I could move this up and down in one plane, and that would give me more chance to hit these, okay, scatters, but it's not going to help me at all with the other scatter. It's not going to make it any more likely that I hit more of them. So I can make myself longer, let's say, in this dimension. And yes, more of the scatter going this way and this way will hit me. But the fact is less of it's this way and that way can hit me. So the stuff going these ways has less chance because I'm not in a standard location where, I'm moving the speed of light. Well, anyway, so you can't overcome the inverse square law by being in gravity longer. It won't fix the problem. That's why it's a velocity equation. It's just about velocity, and you can't change that fact that it's about your velocity. The atom I throw this chalk into space, just get it out of the Earth's gravity. It doesn't change anything about its motion around the sun. It moves at exactly the same velocity I do. The same gravitational force will affect it. So even if I break the Earth into a million little atoms, they all stay in the same, they're still moved by gravity of the sun exactly the same. Their velocity stay, everything, their curve, everything. It's just a velocity. It doesn't, mass, you have to have mass to be affected by gravity, but it's really your velocity that dictates how you orbit something and how you're bent by it. So bending is all just about velocity. So anyway, yeah, so he wrote a bunch of stuff there. I'll read all the stuff he wrote, but again, it's all right. I'll cease to say there's no way the wrong shaped lens can't magnify, because yes, if you have a gigantic lens, all right, and you shoot the object up. But again, you have to project it, which means you make the difference in these lengths of these lines. You have to project it larger. So all the lens images that, again, have a solid object with lensing couldn't possibly be true if it's a galaxy that they're lensing. If the object you're looking at is bigger than the object that's making the lens, there's no hope you would see it because you'd never be able to collect more light. Again, you have to collect more light. You need to increase your view. So where my view from Earth would be, this object would be a very small, take up a very small arc, okay? The arc would be this little shaded area, right? I need to project this image somewhere where I can make the arc big, I can make the image big, so then I can collect more light. That's magnifying. I have to collect more photons, and I don't collect more photons by making a virtual image of the object somewhere in space and then look at the virtual object, the big giant object. So I can only lens in something that has a huge, so if I'm going to lens a galaxy, that is, I'm going to see a galaxy, the object I'm lensing in it has to be preposterously gigantic. And my argument is, it's not like suns, okay? You can't just make the sun bigger and say, okay, there's 70 meter per second gravity here, and I made it 10 times bigger, so now there's 700 meters per second here. That won't work with galactic clusters. Your gravity doesn't get stronger, it gets weaker because you're injecting huge portions of empty space. And so your capacity to create any bending gravity is much, much lower. So as you make the screen bigger, you make the amount of gravity possible much, much, much weaker and much less likely to have any hope of bending light. Alright, I guess that's all I need to say. So there's always this catch it. The whole thing is, a lot of people understand this. I mean, they understand. This is all about this optics stuff with photons and images and understanding that there's an image of everything, just like everywhere. There's an image of this chalk going here. There's an image of the chalk going here. Here. Let me put it here. There's an image of the chalk here. There's an image of it here. There's an image of it here. There's an image of it. It's everywhere all at once. That's why if I take a plain piece of photographic film without any lens, I'll just get a bunch of white. I'll get no image of the chalk. Nothing. Because you have to select what version you're going to get to see the image. You have to take a selection of all of those images, or they'll all end up right on top of each other. And that's actually how they make holograms. But anyway, yeah. So yeah. I mean, optics are really tricky, and so yes, you can magnify something, distant object, with a gravity lens, but there's really specific rules to where you can do it and how you can do it. And I would argue that those rules mean you're out of luck in the real universe, because the bigger you make your screen, the weaker you make your gravity. And you're not going to be able to overcome that fact. Alright, so that's probably enough on lensing for now. Like I say, I'll read the rest of his comment. It was a lot of crap he wrote. So maybe concede some of these points. So I can read some of it now. What the hell? It won't hurt that much. That's not it. Alright, well, he's right that dispersing effect will do something. However, it won't make images impossible to see. Well, again, first you can't see them in the same time. So let's understand, the lens won't fix the time problem. Gravity lens doesn't slow light down, so there's no mechanism to make time corrections. So the photons you will be receiving from your telescope will be photons of an image. The photons from the head will be hundreds of thousands of years older or younger than the photons you'll see from his feet. And that means the location of the object is fundamentally changed, which means it won't be in the same focal length, which means you won't see it. As the focal length changes, it moves out of the right trajectory for you to do all of this mechanics. So if the object moves towards or away from you at all, it'll go in and out of focus and you won't be able to see it at all. Anyway, there's a few things to realize, or at least it is helpful to keep in mind. First, the light bulb star not only emits light in all directions spherically, but each point on the bulb emits light in all directions. So this is just it's good to illustrate this stuff. I mean, it's good to recognize, okay, that an object doesn't send photons. Like I said, all the images of this chalk are all different locations of the chalk are all going, each piece of the chalk is going to all those locations. So when you have an object, just make an object, the point is not only is it all the light spreading, in 180 degrees in a direction or whatever, but each point on the object is sending an image to all locations. So in both dimensions, there's a pixel of energy at any one moment going in all of those directions and all of those places. So it's like a machine gun going like this and then a machine gun going like this. So imagine that they could do both at the same time. It would fill all the spaces. Well, at any moment the photon is taking one of those paths, and then probabilistically that's what it's doing. So every point on the object, not every point, but we could argue every group of atoms of, say, 500 atoms, every hunk of 500 atoms on the surface is deflecting light in all of these directions, either emitting light in those directions or reflecting light in all those directions. So all the directions this way and all the directions this way. That's an important thing to understand. All right, it's more complicated to explain, but consider this image. So that was the image I showed. On the top of the image, you can see the rays from the top and bottom of the candle reaching the eye. On the bottom of the image, you can see the ray okay, so there's no point in really going through all of those without showing the image again, and I don't think that's necessary. I mean, I sort of made the point that it is possible to project the image, to expand the size of the image and send it to a location and have a gravity lens that would bend the light more the closer it is down and bend it less at the top. I'm still not too sure about those angles. But anyway, conceding that. The point would be, though, is that you have to make it bigger to make enough light for you to see it. So you have two things. You're collecting more photons. That means you're covering more space, which means there's a greater difference in the gravity at those two locations. And it's a huge difference in the sense that the projected image is thousands or hundreds of thousands of galaxies across. And there's no way, you can't have a substantial difference in the gravity across a distance that great. But the underlying gravity is so weak that it couldn't possibly make a difference. There's no way you could get enough bending to send the image to an earthling. But anyway, All right, so like I said, I'll read the rest of this. And yeah, that's enough for now. But yeah, there's so many. Like I said, I didn't. A year ago, I was clueless to this whole idea that how critical it is that a magnifying lens is actually changing time. That the photon going through the center is going much slower to compensate for the fact that this line is much shorter than this line. And that, that's part of what makes a lens work, is the very fact that it does slow this photon down so that this distance is equal. So it's just a lot of little details. And this whole idea of projecting a virtual image in space that's bigger than the size of the image that would go to you. Like, say you're looking at my head. The idea would be to make a picture of my head here that's much bigger. And now that bigger picture is closer to you. And that's what magnification relies on, is creating a virtual screen to project an image onto, and then look at the image instead of looking at the object, the virtual image. But anyway, enough on this subject for now. It's not critical to my theory in the sense that I would find it bizarre if photons really were bent by light, and we have to have some sort of excuse for why they would be, why photons are bent by gravity. But again, the evidence is not in any way decisive. All the lensed images from space have mathematical flaws. Another thing to point out, like I said, the other video I played and showed where the guy, looked at the lensed images and could see artifacts. Okay, so there was a blob of light that was sort of shaped like this. It had 3 elements to it. And then he saw the same blob, okay, and these elements lined up. So one of them was in this plane, and one of them was in this plane, in the lensed image. Now, there's no way that you would have a picture of something, okay, where you would turn the image in the lens. The lens would see a different image here than it would see here. It couldn't turn it, okay, sideways. You wouldn't see, like, the person being lensed this way, okay, here, and see the person lensed this way here. That wouldn't happen. They would be lensed appropriately. You wouldn't be able to change their orientation with the lens. The lens can't do that. So obviously the artifact is that. It's an artifact being created by something that's creating a reflection, an image of it in this perpendicular plane, but it can't be the same thing because it's the wrong image. In the wrong one of them's the wrong image in the wrong location. Alright, anyway, so till the next time. But lots of flaws with all of those images. You can see the obvious lack of symmetry in the gravity. If it's strong enough to bend the light, it should be very symmetrical gravity, and it's not, and blah 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 blah. So till the next time and such. I just don't want to emphasize it, because to me it's not fundamental to the theory that I prove photons aren't bent by gravity. I'm just saying it is kind of fundamental to this whole analysis, that you have a tiny bit of evidence that might indicate it's possible or it happens, but it's a tiny amount of evidence. It's nothing like the kind of evidence they should have to make such an assertion, especially the assertion that light is bent twice as much.